Hi, good morning, everyone. My name is Eri Vokshi. I'm a senior product engineer at Sika US, focusing on CFRP and corrosion products. I'm presenting today on an exciting technology, which is post-tensioning with carbon fiber solutions. I'm sorry I'm not able to attend the conference in person. I unfortunately tested positive for COVID recently, but I'm very appreciative of the NCPP organization team for allowing me to submit my presentation via this recording. So I'll jump right into the presentation. A brief outline of what I'll be covering today. I'll talk about why structures need to be strengthened and typical strengthening methods available in the industry. I'll also mention how external post-tensioning works, including advantages and disadvantages of it. And then I'll dive into the solution itself, the technology itself, which is post-tensioning with carbon fiber, the anchoring methods with it, as well as different some really unique case studies from across the globe. So why do structures need strengthening? As we start this discussion on why and where we use these products, let's just take a look at our infrastructure report card that's issued by ASCE every year. The latest one issued was in 2021, and it paints quite a dim picture of our infrastructure. Currently, 42% of all the bridges are at least 50 years old, and 7.5% of the nation's bridges are considered structurally deficient. So that's pretty alarming. The total infrastructure needs to address all these issues would be around $6 trillion for the next 10 years. But structural deficiency can take several forms. You know, the most obvious one is the weathering one, but we can't forget the increase in demand of our bridges, for example. Many of them need their capacity increase to meet today's traffic demands. Similarly, structures need strengthening due to a need to restore strength lost from damage or deterioration, increasing load-bearing capacity, correcting design errors, improving seismic performance, or even blast hardening. The most typical strengthening method used are externally bonded FRP systems or steel plates. I would say this is probably the most commonly used strengthening method nowadays. And though a lot of it used to be with steel, more than 80% of it has shifted to be done with FRP, which is exciting for our industry. Then, of course, you have section enlargement because there's limitations with FRP that and steel that that they're not always a good solution. The section enlargement is a lot more intrusive to a structure because you're adding a lot more weight to it, and it takes much longer to implement. Another strengthening method is external post-tensioning. This is the topic of the discussion today. Traditionally done with steel, we're now introducing a technology where it can be done with FRP as well. And then finally, supplemental reinforcement is also another strengthening method if all the other ones don't work. This is a bit more expensive and sometimes, with limitations on space, depending on where the structure is, it can be quite difficult to implement. So as we dive to learn more about the PT system, I'm going to start with the basics by defining what an FRP is, since this technology falls within those with FRP offerings, and then we'll go deeper into post-tensioning with FRP. So an FRP system is in a combination of a fabric and a resin that form an extremely strong monolithic material, which is designed to share the load and the stresses with the host substrate. And so externally bonded FRP systems are the ones that are, as I mentioned, as the word describes it, bonded, whereas a post-tensioning can be bonded or unbonded. And we'll talk more about that in the future slides. And then last comment, reinforced concrete is a composite itself. It's a combination of your matrix, of the steel itself, the paste aggregate, and all that good stuff. And so when you're adding FRP to it, you're creating quite a complex system. So understanding how to properly design with it is quite critical and requires an experienced and knowledgeable engineer to do so. So there are a variety of strengthening FRP products in the market, many which are unique to Sika. And I'll start and just give an overview of all of them. The most commonly used one is probably the wet layup systems. These are the carbon fiber fabric systems that are installed when the fabric is still has been saturated and it's as the term says, wet. And then once installed on a primed surface, it cures in a hard shell, giving the strengthening that's required. Another strengthening FRP system is pultruded plates. These are the carbon fiber plates that are very high strength and stiffness. They're manufactured in a controlled environment. They do have a bit of memory to them, hence, pre-cured plates. And so they're usually only installed for flat applications or bridge girders. The plates actually are utilized for the post-tensioning FRP systems, we'll talk more about. Another system that's worth knowing about is the near surface mounted rods. These are carbon fiber rods that come in a variety of diameters and are usually preferred to be installed as a top surface application. We've used them for deck stiffening. The advantage to them is that they're not corrosive, and so you can install them very close to the surface of your structure. Another FRP system is post-tensioning FRP. I'm not going to go into it much now, since this is the topic today. And then finally, worth mentioning is the FRCM system. This stands for Fiber Reinforced Cementitious Material System. These are this is a carbon fiber grid product that's embedded in a cementitious matrix. The advantage to it is that it's very breathable. It can be installed in very large surfaces quite fast. And it has, and also can be installed in a pretty roughened concrete substrate, since, again, you apply the mortar and then the carbon fiber grade and then finish it off as well. The disadvantage to it is that it provides less capacity compared to traditional FRP systems. Okay, on to our discussion about external post-tensioning with FRP systems. So I'm going to start by comparing what external post-tensioning versus traditional FRP systems are. So when we're talking about externally applied FRP systems, we're referring to basically a passive strengthening method. And what a passive strengthening method is that once FRP is installed on a structure, the structure itself needs to see a new load for the FRP to engage and to provide the strengthening that's needed. External post-tensioning, on the other hand, to refresh your memory, provides active reinforcement, and it involves usually attaching traditionally steel cables or plates to an existing member at discrete locations, and then special anchors are usually designed to anchor to perform the post-tensioning, and then of course the tendons or FRP plates are post-tensioning the field to the desired force. But what I mean by that is that with active strengthening, once the post-tensioning is applied or that force is introduced, it automatically relieves the stress in your structure, providing the additional strength that's required on the structure. Because of it is an active strengthening method, it does address deflection. With traditional FRP, though, we know that it adds some intrinsic stiffness to the structure. It's really hard to quantify it, and really none of the design guides that we have available provide guidance on how to address deflection with a passive strengthening method. With an active strengthening method, this can definitely be done as you're introducing a PT load to your structure. All right, the last few words about external PT and the difference between FRP PT. As I mentioned, usually external post-tensioning was done with steel, and with anything else that's steel, it is corrosive. External post-tensioning with steel is corrosive. It's heavy. There's a lot of fabrication that's required and can be very high maintenance. Whereas with FRP, you're looking at non-corrosive and chemically resistant material that's lightweight. We'll show some videos here shortly on how easy it is to install. We also have lots of testing that show that there's no creep and slip behavior, and the plates can come in limited length. All right, so let's talk about the CarboStress PT system. The system itself has been around for more than 20 years. It's mainly been used in Switzerland. We have projects across the globe with it. We've actually even done 2 pilot projects, one in the US and one in Canada, both of them successful, but the majority of the experience has been, as I said, in Switzerland and other areas of the country. The system can be used for many applications. The majority of the application has been in bridge strengthening, but we've also done projects with strengthening of industrial and high-rise buildings, lots of seismic strengthening, very good applications for that. and then also reinforcement of water tanks or silos. The CFRP post-tensioning solution is very similar to a standard steel external post-tensioning system. It involves a fixed anchor side and a movable anchor side. On the movable anchor side, we usually install a hydraulic press behind the anchor, and then with that, we pull the head of the anchor backwards, and we can introduce up to 50 kips of post-tensioning load to it. Now, there's several types of anchors that are standard that we offer with our system. The first one here is the one that we've been showing in the previous pictures. This is what we call our shear pin anchor. This is mainly used for concrete reinforcement, such as walls and ceilings, where you do have clearance from the reinforcement, because you do need about 4.7 inches of embedment into the concrete itself for this type of anchor. But with this one is that the way it's been designed is that all the post-tensioning load is carried by the internal reinforcement of the structure itself. Another anchor head that's worth mentioning, another anchor type that's worth mentioning is the one shown in here, which has been designed for masonry walls, but we've also used them for bridge applications. In this case, the threaded rods go through the slab and anchor the plate on the other side of the wall. The advantage here is the force, the post-tensioning force is transferred into the slab instead of onto the, and provide the tensile stress onto the wall, but not introduce compressive stresses onto the masonry wall. This is, as I said, also applicable in some cases, for example, for pier caps, where you might want to take the post-tensioning load on the side of the pier cap to prevent, for ease, I guess, for ease of installation of the anchor heads as well. Now, as I mentioned, we've had over 20 years of experience with this system, so we've come up with many different types of anchor heads for the application, or anchor types, I should say. For example, this is a special anchor that was designed for areas where there's high reinforcement inside, where in this case we're a U-channel type of anchor has been designed to go around a girder. We'll talk more about this case study later. And then all of the post-tensioning force is carried superficially onto the structure with a shear bar that goes through the beam itself here. The overall components of the system, if you haven't figured it out so far yet, includes the carbon fiber plate, the anchorage itself, which is the steel portion of it, and then also the anchor head, which is what the proprietary thing is in this system. The anchor head is manufactured by a company in Switzerland called Stress Head, and they're really the brains behind this technology, and we work closely with them. So as I mentioned, the way we approach a project is, if you have something that's interesting, this might be good application, and you bring it to us for a review, we'll look at various anchors that we have worked with previously, and if none of them fit, we can always customize a solution, so that the system can be installed properly. The installation process is quite fast and very efficient. Basically, it involves drilling the area where the anchors have to be installed, chipping, for example, in the case of the shear pin anchor, the section of the concrete, installing the anchor, injecting it, and letting it sit. Now, the post-tensioning plate can be installed either bonded or unbonded. We usually recommend that it is installed bonded for mechanical protection. In the video here, you can see how the plate is being primed with an epoxy to be bonded onto the structure. This is very similar to, if you're familiar with the plate system, with Sika's plate system. We do this for traditional externally applied FRP. The same application is done here as well. We'll see this case study further in detail, but this video here shows the simplicity of the installation of the plate. In this case, you can see that the contractor is installing the fixed side of the anchor, making sure that it's bolted in properly. And then on the other side, they've also anchoring it in, and now the post-tensioning process starts. You can see continuously they're measuring the post-tensioning forces to make sure, well, I should say the deflection on the plate to make sure that the post-tensioning forces are achieved. As I mentioned, the 50 kips post-tensioning load that we recommend, the maximum load that we recommend, that's about 50% of the overall capacity of the FRP plate. So we have quite a bit of cushion in terms of the design with these systems. Here's a close-up video of the post-tensioning process. You can see the hydraulic jack introducing the post-tensioning load onto the plate, and the two bolts on the side of the anchor pulling outside with the load. The post-tensioning process is done in multiple steps to make sure that we're not exceeding the required or the designed post-tensioning load. And then once the post-tensioning load is achieved, the bolts or the washers are tightened in, and the hydraulic jack is released, and that's it. And the post-tensioning force is introduced to the structure and stays in place for many, many years. All right, on to several project references. As I mentioned, the system can be installed for longitudinal and transverse reinforcement, as well as for substructure reinforcement. We've used them for shear, for noise barrier walls, pier heads, girders, of course, etc. But the most common application, or I guess the case studies that I'll be showing you here are for damage to an existing structure, usually for higher load requirements, as well as corrosion problems. The first project here, a railroad company recently bought heavier trains and required strengthening of the bridges to address the new loads. But as you can see from the picture on the top right-hand corner there, the concrete thickness on the box girders was very thin at the bottom. So for this reason, special anchors, which were quite large for our application, had to be designed to make sure that the existing cables were not damaged and the stresses on the concrete were distributed properly at the ends. The installation videos of the systems earlier that I showed were from this project, actually. Another project we're showing here is one in France, where precast elements were hit by a truck on the bridge. The truck destroyed the entire beam with the existing reinforcement, and the job was to replace the missing strength of the PT cable here. In this case, this is when we utilize that special anchor, design anchor that I talked about. There was not much space either to work between the beams, as you saw in the pictures there, so we had to be quite creative in coming up with a solution. What we designed is a PT system that would go on both sides of the beam in case, you know, the cars hit it again, because as you know, many times bridges get hit on the same area, or the same bridge gets hit multiple times by trucks or cars. So in this case, as I mentioned, we use this what we call the shear pin anchor, where the PT stresses are introduced superficially to the concrete surface on the side. There's a shear bar that goes about 1 inch into the surface of the concrete, but then all of the PT load is carried through this anchor pin, basically, that goes through the beams, avoiding all the reinforcement along the way as well. The post-tensioning here was done with two jack hammers, and it was done simultaneously to achieve the proper reinforcement. And you can see here also we introduced U-wraps for shear strengthening of the girder as well as to provide additional strength for the concrete itself due to the high post-tensioning loads being introduced in the ends of the beam. Another bridge application, this is in Switzerland, where coupling joints were being damaged due to moisture. In this case, this particular bridge that was designed and built in the 70s was very, very long and include multiple coupling joints. And the coupling joints over the time had started showing deterioration signs, and that could be, that's a dangerous thing because it could also damage the rest of the post-tensioning onto the bridge. Now, another limitation on this bridge is that it's a major bridge, or it's a bridge that goes over major railroad tracks, as you can see in the picture here. So that there had to be very limited disruptions during the repair process. And so what the engineers decided to do in this case is to introduce the post-tensioning system around the joints to make sure that they stay close, tight after the repair, of course, and make sure that no further deterioration is introduced in these areas. So in this case, we installed the post-tensioning system in a staggered method. And again, this main reason behind this is so that the stresses are not concentrated in one area. And this was all done within 2-day time frame. And then I guess just to give you an overview that the post-tensioning system can be used for many applications, including buildings. I mentioned the seismic, that's a big one, but we've installed them on slabs, we've installed them on beams, we've addressed serviceability issue, strengthening of pre-stress structures, as well as general deterioration. Another good application that you might find interesting is their application in silo or water tank structures. The picture on the right is a project that we recently did in Tel Aviv. In this case, we've tensioned an entire tank with 8 systems. You can see that the post-tensioning the post-tensioning anchor side was tied together. This was a special design for this application, and the idea was, after the repair was done properly, of course, that the cracks would not further develop, and they would stay close after the by introducing a external post-tensioning load. To avoid friction losses, we had to tension obviously both sides at the same time. Another application outside of the bridges, but that addressed serviceability, was the one in Vienna, where a wall in a casino was removed, but there were still 2 columns that had to be addressed that were awkward in the room due to change in use on the structure. If removing those 2 columns, it would have resulted in very large deflections of the slab, and so the post-tensioning solution was utilized to prevent deflection, and so that the columns were removed. So this picture is right after the PT system was installed and before the columns were cut out to open up the space. Okay, last few words on design and tests. We've done multiple tests at the University of Lucerne in Switzerland with different anchors and different slabs and slab strengths. We've also performed fatigue testing for the entire system at the Milan Polytechnic Institute in Italy. We also have done long-term tests for the past 10 years to extrapolate up to 50-year creep and relaxation behavior of the system. And what we see so far is that there is no loss of tensioning force over the years. One of the main reasons we think this is the way the anchor head holds onto the plate itself. That's all a mechanical type of bond. There's no mechanical type of anchor. There is no bond to it, and that's what the proprietary portion of the system is. So as I mentioned, we've done projects for the last 20 years and have quite an extensive experience with it. Hopefully, as you went through the presentation, you saw that the system is very lightweight and super fast to install. It is a corrosion protected system, so you don't have to worry like with steel about corrosion attacks. And with more than 20 years of experience, we have developed so many different types of anchors that I'm sure we can find a solution for your next project. And with that, I appreciate your time. Again, I wish I was there in person to answer questions. Hopefully my colleagues are there, that they can either take your questions, but I'm more than happy to discuss this further with you if you want to reach out to me via email. Here's my contact information, and hopefully I'll see you on the next show. All right, everyone. Thank you and take care.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.